Hey guys, all right, we're picking up here with chapter 18, which is basically an extension of the thermo that we've already talked about, okay? So you know how last semester we spent a chapter on thermo? Well, this basically picks up where that ball left off rolling, okay? But I want to take a few minutes to kind of quickly remind you about some of the more important things we learned from that chapter. But this chapter does, for the most part, it is separate in a way, but it does expect you to remember some of the things that we talked about before. So let's talk about that. Let's make sure that we remember everything from those previous chapters. Well, number one, you've got to know the first law of thermo. I mean, this is a foundational idea in the field of science, and that is the fact that energy cannot be created nor destroyed. Energy is conserved. So take a look at the slide. We're not saying that the energy of the universe is zero. We're saying that the change in energy of the universe is zero, meaning energy is constantly transforming and shifting from the systems to the surroundings, but it's conserved. It's a conserved transfer, which means there's no energy loss. So the energy that the universe has today is exactly the same amount of energy the universe had when it was created. Okay? And remember, we use capital E to represent energy, and this capital E means all of your kinetic and potential energies kind of summed together, right? And the system is the thing that we're interested in studying, and the surroundings is essentially everything else, right? And we talked about how the easiest way to calculate delta E is to look at heat and work, right? Because those are the two primary ways that energy is exchanged between the system and the surroundings. And we talked about really it comes down to the sign of these values, right? When heat is lost from the system and gained by the surroundings, we always look at the system's perspective. So the system has lost, so Q is negative. If the system gains heat, which means the surroundings have lost, then Q is positive because, again, we're looking at it from the system's perspective. For the work, you guys remember I told you the analogy about if someone brings me a glass of water, I'm feeling pretty positive because I didn't have to do the work. So someone did the work for me. The work was done on me, the system, so positive. Or if I have to get up and get my own glass of water, then I'm feeling kind of bummed, which is what I have to do all the time now because I'm stuck in my house by myself, not going crazy. Okay, maybe a little bit, but come on. Yeah. Then I'm feeling kind of negative, right? Because I had to do the work. And then depending upon the numerical values of these two things and the potential of having different signs, delta E could be positive or negative. Now, if Q and W are both positive, delta E is automatically positive, right? If Q and W are both negative, then delta E is automatically negative. But it's when they differ in signs that you have to look at their numerical values to actually figure out what delta E is going to be. Okay? All right. So because delta E depends only upon the initial and final states, we say that the change in internal energy is a state function. Remember, basically anything you can represent as a delta and it makes sense to represent it as a delta, that's a state function. So delta P, change in pressure, delta T, change in temperature, delta V, change in volume, right? These are all state functions. But heat is energy in transit, and work is energy in transit. So those can't be represented as deltas, right? Because they are the change, which means Q and work are not state functions, right? They are not state functions. But what they equal is a state function. So Q by itself, not a state function. Work by itself, not a state function. But when you sum them up, it is a state function. Okay? So what does that tell you? That tells you that just because the things that you're manipulating together aren't state functions, that doesn't mean that they can't make a state function. Okay? But if you flip that, it's not the same. Because if everything that you're adding together is a state function, then what it equals must also be a state function. So it's not the same both ways. We talked about this concept of enthalpy, right? About how 99% of the systems we look at in chemistry are open atmosphere systems, and how if it's open atmosphere systems, then the only work that happens is P delta V. But if P isn't changing, then delta H is just equal to Q, right? So delta H equals Q at constant pressure, all right? And delta H is enthalpy. And we talked about how delta E equals Q at constant volume, right? So if you're looking at constant pressure, then Q is going to give you delta H. If you're looking at constant volume, which would be bomb calorimetry, right? Constant pressure is coffee cup calorimetry. Then you get different values as far as what they're equal to, okay? And you can assign the terms endothermic and exothermic, right? Endothermic means into, so heat's going into. Exothermic means heat's leaving, going out of the system. All right. Now, we've talked about spontaneity a little bit before, but let's talk about it more in detail, right? So what a spontaneous process is it's something that's capable of proceeding without any help from you, right? If you burn popcorn, I don't care how many gods you pray to, when you open that microwave, the whole room's going to smell like burnt popcorn, right? Because it is what it is. It's a spontaneous process. Gases expanding to fill their container is always a spontaneous process. So if you had two vessels connected together and it was closed and there was only gas in one side, if you open it, that gas is going to evenly distribute, right? That is how it is. But what do you notice? So the expansion of the gas is spontaneous, which means it proceeds without any energy. But going back, that's not spontaneous, which means that is going to take energy. So the opposite of every spontaneous process is a non-spontaneous process, and that's going to require energy input to proceed. Okay, so like if you leave a metal tool outside, it's going to rust in the dew in the atmosphere, right? And your dad's going to be super mad at you about that, right? Because you're ruining his tools and stuff. Now you can get the rust off because all rust is iron oxide, but reversing the rusting process, you need to do something called electrolysis. And we'll talk about that next chapter. But the problem with electrolysis is this: when it comes to iron, the cost of iron, what it's worth, is not that much. So for the most part, it's just cheaper to throw the item away, especially if it's like a nail or a tool, and just get something else, right? But a bridge, first of all, you don't want a bridge rusting in the first place. But if a bridge does rust, you're not just going to throw the bridge away, right? So we need to have a way to sort of reverse that process, and we do, and we'll talk about that next chapter. So, and conditions like temperature and pressure, they're important in determining spontaneity. Like if you take ice out of the freezer and you set it on the table or you put it in a glass, the ice is going to melt. Why? Because you've put it in a temperature where the natural form is a liquid, so it is spontaneously going to melt. If the ice stayed as ice in your house, that would be very unsettling, because that means that you're living in an environment that's 0 degrees Celsius or below, or I would get the heck out of there because aliens are involved, because that does not make sense for ice not to melt at room temperature, right? Vice versa, how do we make ice? We pour water in an ice tray, we put it in the freezer, because in the freezer it's below 0 degrees, so the water is going to spontaneously freeze and make ice. Now, but I want to be very clear here. Thermodynamics and kinetics are two very, very, very different processes. Just because something is thermodynamically favored does not mean it's going to be kinetically favored. What do I mean by that? Just because something is going to happen because it's lower, if it's lower in energy, it's going to happen, right? If it's going from a higher energy state to a lower energy state, it's going to happen. But that doesn't mean it's going to happen at a rate that you can observe, because kinetics and thermo are separate. Like, it's spontaneous for diamond to turn into graphite. So why do we spend? Why is diamond a precious resource? Why is there so much bloodshed? I mean, literally, there are types of diamonds called blood diamonds because the amount of blood that's been shed over getting them. And why? If it turns into graphite? Well, because it's not going to turn into graphite in our lifetime. Okay? Or anybody else's lifetime for that matter. It's super slow. Okay? So what am I saying? I'm saying thermo tells you the direction, which means, is it going to proceed in the forward direction towards the production of products, or is it going to proceed in the reverse direction towards the production of reactants? And it lets you know how far it's going to move each direction, but it doesn't tell you how fast it's going to move. Okay? Think of it this way. Imagine reading the first chapter of a book and the last chapter of a book. That's thermo. You get a pretty good idea of the story, but you miss all the nuances of what's happening. The nuances are the kinetics, how you get from chapter 1 to chapter 20 or whatever, right? But the nice thing that we're saying here, though, is that you can study these two things separately. You do not have to study the thermo at the same time that you study the kinetics. And that means you don't have to worry about them interfering with one another. Now, in a junior level P-Chem class, though, you're going to learn about thermodynamics and kinetics, right? So P-Chem is physical chemistry. You're going to learn about both of these, but the sections are separate. But the idea is you have to learn them both to understand the whole story of what's happening. Okay? All right. So that's the end. Well, let's do some practice. So, and then this will be the end of this video. So what we're going to do is I'm going to pop up a process and you're going to tell me if it's spontaneous as written, spontaneous in the reverse direction, so the opposite of what's written, or if it's not going to be spontaneous at all. Because if you have a chemical equilibrium, that sucker ain't spontaneous. It's not moving in any direction. All right. So if you take a piece of metal that's super hot, so it's heated to 150 degrees Celsius, and you add it to water, and then all of a sudden the water gets hotter. Do you have to do anything to make the water get hotter? No, right? The heat transferred from high to low spontaneously. So this is a spontaneous process. Now the opposite of this, though, would be non-spontaneous. Yes, absolutely. All right, what about this? What about the decomposition of water into hydrogen and oxygen gas at room temperature? Yeah, no, that's not spontaneous, right? That would be petrifying if you were going to take a sip of your water and then it all of a sudden like broke apart and was no longer water, right? I would take off running because that's not normal. Last one. Benzene vapor at a pressure of 1 atmosphere condenses into liquid benzene at the normal boiling point of benzene. The definition of a boiling point is when vapor pressure equals atmospheric pressure. Another way to define it is when the two phases, liquid and gas, are in equilibrium with one another. So if they're in equilibrium, it's not spontaneous in either direction, right? We are just in equilibrium. All right, so end of video 1. I'll see you in video 2.